Hello everyone, welcome to lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. I'm an assistant professor at Comsets University, Islamabad campus. These slides have been edited from these two sources given here. The topics of this lecture are instructions set of Intel family of microprocessors. In particular, the focus is on instruction setup 8086 microprocessor. Also, string manipulation instructions, including repeat prefix, MOVS, and compare string instructions are also discussed in this lecture. Briefly about the instruction set of 8086 microprocessor. In 8086 microprocessor, there are 6 types of instructions in the instruction set of 8086 microprocessor. These types of instruction set are here. The first type of instructions for the 8086 microprocessor is data transfer instructions. These instructions are responsible to transfer data between registers, memory, and input and output devices. For example, these instructions can transfer data between registers, from register to memory, from memory to register, from input and output I/O devices to memory, and so on and so forth. There are arithmetic instructions to perform arithmetic operations like addition, subtraction, and logical instructions perform logical operations like AND, OR, exclusive OR. String manipulation instructions, which is also the topic of this lecture, they are responsible to manipulate string data. For example, to move string data within the memory, or to load or to store string data. Also to compare string data. Processor control instructions control the status of the processor. For example, to set the carry flag, or to clear, or to set or clear the direction flag. Control transfer instructions change the flow of control when the microprocessor is executing a program. For example, it can take control from one place in the program to another by using jump instruction. So jump and call instructions are in this type of instructions. String manipulation instruction, as the name specifies, these instructions are responsible to manipulate string data. String is basically a sequence of bytes or words, or it can be a sequence of double words or quad words in 80386 and later microprocessors. 8086 and above microprocessor include instructions for string movement, to move string data between the memory locations, to compare string data, to search or scan string data, to load accommodator from the memory, or to store accommodator into the memory. So for all these operations, there are string instructions available in all microprocessors. Also, there is a repeat instruction prefix. That prefix is represented with REP. This repeat prefix, when used, causes the string instruction to be repeated multiple times. So the instruction is executed multiple times with this prefix. There are some conventions with string instructions. For example, the string instruction is used with or ends with letter S or SB or SW. And these letter means S stands for string. So for example, MOV is common data transfer instruction, but when S is used, it become a string manipulation instruction. So MOVS is a string manipulation instruction. And additional letter, for example, B and W are used for to operate on string byte or operate on string word. And this happens in the 8086 microprocessor, but let me highlight them. Okay, so in later microprocessors, can operate on a double word string data and also on quad word string data. So for them, there are D letter is used for double word, Q is used for quad word. So it's easy to remember these variations of string manipulation instruction. For example, MOVS means string manipulation instruction, MOVSB means a string manipulation instruction or string transfer instruction on bytes. MOVSW would mean to operate on word or 16-bit up string data. MOVSD would mean operating on double word. MOVSQ would mean operating on quad word or 8 bytes of string data. In string manipulation instruction, there are effective addresses just like other addresses, but these effective addresses are not part of the instruction. These effective addresses are provided, are used implicitly. They are not directly provided as part of the instruction by the programmer, but these addresses are taken from source index register and destination index register. So in string manipulation instructions, either there is a source or there is a destination, or there are both. In any case, if there is a source of data, then source is normally the data segment of the memory, and the offset address for the data segment is provided through the source index register. While if there is a destination used with the string instruction, then the destination is normally the extra segment, and the offset addresses for the destination operand is provided or stored in the destination index register. So source index register is used for to provide the offset address for the data segment, while destination index register is used to provide offset address for the extra segment. And if there is an instruction that is using only data segment, then only SI would be used. And if the instruction is using only extra segment, then DI would be used with extra segment of the memory. And also, as these instructions are normally repeated, with every repetition or after every execution, the value in these offset registers, source index and destination index registers, are either automatically incremented or decremented. There is a flag in the flags register of the microprocessor. The flag register is the direction flag, represented with D or sometime with DF. So the value of that direction flag determines if the source index or destination index would be incremented or decremented. So if the direction flag is 0, then this mode is called auto increment mode. And by auto increment mode, we mean that each time the string instruction is executed, source index and destination index are automatically incremented by 1 if the instruction has operated on 1 byte, or it is incremented or decremented by 2 if the instruction has operated on 2 bytes. For example, if the instruction is used with SB, then that would mean that the instruction has operated on a single byte, so source index and destination index would be incremented or decremented by 1. But if the string instruction is used with letters SW, then that would mean that 2 bytes have been operated on. So source index and destination index registers would be either incremented or decremented by 2. As the direction flag is 0, so in this case the auto increment mode would be set, and SI and DI would be incremented by 1, 2, or depending on the number of bytes that you have been operated on. For example, in the later microprocessors, there are other directors, for example, SD, that would mean double word. So in that case, SI and DI would be incremented by 4 because 4 bytes have been operated on. And in case of in case of code word, 8 would be added with the source index and destination index. Similarly, if the direction flag is 1, then that means auto decrement mode has been set. And auto decrement mode means that each time a string instruction is executed, source index and destination index register are decremented by the number of bytes that have been operated on. So if 1 byte instruction is used, then the decrement is 1, and if 2 bytes instructions are used, then SI and DI are decremented by 2. And as I said, with case of DF, when DF is equal to 0, if the string instructions are used with a double word, then the decrement is 4. If they are used with quad word, then the decrement is by 8. That is, the source index and destination index are 8 is subtracted from source index and destination index. So basically, this flag, direction flag, basically sets if the offset address are increasing or if they are decreasing. So it sets the direction. Repeat, as I said, REP is it's a prefix normally used with the string instruction except load S. There are different forms of repeat instruction. The popular are repeat as F0 or repeat F equal. They are the alternative of each other, so either of either of these forms can be used. So repeat F0, then there is a string instruction followed by this repeat F0 or repeat F equal. So the instruction that is followed would be repeated. Its execution is repeated as long as the counter value is equal to 0, and as long as the 0 flag is 1. The string instruction is repeated, and after each execution of the string instruction, the counter, which is CX, is decremented by 1. So this counter is set before a repeat instruction. A repeat prefix is used with the string instruction to execute the string instruction as many times as the value in the count register, and this value is set by the programmer. Similarly, there are other forms of repeat prefix, and that is repeat if not 0 and repeat if not equal. So these prefixes would cause the string instruction to execute as long as the counter value is not 0 and the 0 flag is 0. The 0 flag was 1 here, and the 0 flag is 0 here because here the condition is different. So repeat while not a 0 means that the 0 flag is not 1. That means the operation did not result in equal condition. Or a repeat while not equal, they're the same. So both of these prefixes would cause the string instruction to execute as long as the count is not 0 and the 0 flag is 0. And each time when the string instruction is executed, the counter is decremented, and eventually the counter register will have a 0, and that will make this loop to break. MOVS instruction is similar to the move data transfer instruction, but this instruction is the only instruction that is responsible to transfer string data within the memory. So memory to memory transfer is not allowed with MOVS instruction, but it is allowed with MOVS instruction, and this is the only instruction that allows memory to memory transfer. Here both source and destinations are involved. The string data from the source, which is normally the data segment, is transferred to the destination location, which is normally the extra segment. And when we are talking about the source and destination, the source, the offset address for the source is normally provided by the source index register, and the offset address for the destination is provided by the destination index register. So here is the calculation for the physical address. In case of movement from the data segment to extra segment, the physical address for the data segment is MA, that is the memory address, and that address is calculated by taking the starting address of the segment from the data segment register, as we used to do with the other instructions. And that is the content from the data segment is taken, and it is left shifted by one hexadecimal digit, or that is equal to multiplying 16 in the hexadecimal in the decimal system, or by left shifting 4 positions, 4 binary digits, or by introducing 4 zeros from at the rightmost positions in the binary. So if introducing 4 zeros in the binary, or introducing 1 zero in the hexadecimal at the least significant position, is equivalent to left shifting or multiplying 16 in the decimal system. So this operation would make the 16-bit value from the data segment as 20-bit address. And then to reach to a specific location within that segment, an offset address is also added. So the offset address is for the data segment is always provided through the source index register. So summing the two values would give us a memory address, and this address, if we are talking about 8086 microprocessor, then this would be a 20-bit physical address for the data segment. And next is that address, the memory address calculated here is the source address of the data transfer, and then we have to calculate the destination address. So microprocessor would calculate the destination address as follows. It would take the 16-bit value from the extra segment, because the destination is extra segment, and it is left shifted as before, and are multiplying 16 in the decimal, and then the offset address, which is taken from the destination index register, is added, and a 20-bit physical address is calculated. This E subscript denotes the extra segment. So after the microprocessor has the 20-bit physical address of the source of the data and 20-bit physical address of the destination of the data, then the microprocessor would transfer a single byte of data from the data segment memory location addressed by the source index, and that address is the MA address calculated here, and a single byte is transferred from this data segment address to this extra segment address. So from the data segment, one single byte is transferred to the extra segment of the memory. And as I said earlier, the direction flag is also important. So if the direction flag is 0 while this instruction is being executed, at that moment, if the direction flag is 0, then the DI and SI are incremented by 1 because a single byte has been transferred. This B denotes that a single byte data is transferred. So the microprocessor knows that a single byte has been transferred. So the source index and destination index registers are incremented to point to the next locations in the two segments. Auto increment mode, and if at that time the direction flag is 1, then that would mean the auto decrement mode is set by the programmer using some processor control instructions. So in that case, as the direction flag is 1, auto decrement mode has been set, so that would mean DI and SI are decremented by 1, and the reason is because a single byte has been transferred. Similarly, if 16-bit data is transferred from data segment to extra segment, that 16-bit data transfer is represented here with this W, that mean word. So MOVS W would mean that it is a string instruction, data transfer instruction, and as 16-bit data is being transferred. So the physical address calculation happens as before. The physical address of the data segment, which is the source of data, is MA. The physical address of the destination of data is the physical address MAE, that is in the extra segment. And then microprocessor would transfer the address, the byte at the physical address MA to the physical address in the extra segment MAE, and the next byte would be transferred from MA plus 1, which is the next higher address of the physical address of the data segment, and that byte is moved to the next higher address in the extra segment, which is represented with MAE plus 1. And after this transfer, depending on the direction flag, if it is 0, then that would mean that the auto increment mode has been set, and by that we mean that the direction, the destination index and the source index registers are incremented because the auto increment mode has been set. So if D is 0, then auto increment mode is set. And when as the auto increment mode is set, the two index registers are incremented by 2, and the reason is 2 is added with them is that 2 bytes have been moved. And if the auto decrement mode is set, that would mean direction flag is 1, then the auto decrement mode is set, and source index and destination index registers are decremented by 2 because 2 bytes have been transferred. There are different forms of MOVS instruction. These are the assembly language instructions, and here is explanation of the operation that these instructions perform. So MOVS B, as we just discussed it, it is a string instruction that moves a single byte of data from the source index from the data segment memory location addressed by the source index register to extra segment memory location addressed by DI, and after this transfer, DI and SI are incremented by 1 or decremented by 1 because it is a byte transfer, and we do not know here if the direction flag is 0 or 1. Depending on the direction flag, the index registers are incremented or decremented. And if the letter W is used, then that would mean 16-bit data is transferred from the data segment memory location addressed by SI to extra segment memory location addressed by DI here. And the segment index registers are decremented or incremented depending on the value of the direction flag. And these two instructions are available in 8086 microprocessor, but in 80386 and above, they can transfer multiple bytes, even more than a word at a time. So MOVS D means double word is transferred, and MOVS Q would mean quad word is transferred. So the transfer always happens from the source index register to source index from the data segment to extra segment, and again the source index and destination index registers are used there to provide the source address for the source, offset address for the source, and offset address for the destination. There are some different forms of MOVS instruction. and there are two arguments are used just like the move instruction, but these two arguments would identify if the transfer is a byte or if it is a word or if it is a double word. Here just S is used to identify that the instruction is a string instruction, but none of the letter B, W, D, and Q are used with it, and instead this information is taken from the other two arguments. For example, here MOVS byte 1, byte 2, so it's a string instruction and it would transfer a single byte of data provided if the operands byte 1 and byte 2 are bytes. If they are of size byte, then this instruction would move a single byte of data from the data segment memory location addressed by SI to the extra segment memory location addressed by DI, and after this transfer the segment index registers are incremented or decremented by 1. And similarly, if these operands are a word, then it would transfer or it would move 2 bytes of data, string data, from the data segment memory location addressed by SI to the extra segment memory location addressed by DI, and the DI and SI would be incremented or decremented by 2 depending on the direction flag. And if the operands are double words, then double word data is transferred from the data segment memory location addressed by SI to the extra segment memory location addressed by DI. So there are different forms for the MOVS instruction, and I just talked about these instructions. Here we have a simple program or procedure that is responsible to move bytes, all bytes of block A to block B. So we have two blocks of data, string data. One is represented with block A and the other is named or represented with block B, and both of these blocks are defined in the data segment. So remember that so far we were talking about that MOVS instruction is transferring data from data segment to extra segment, but we can override the destination segment and can make it happen to be a data segment as well. So suppose block A and block B are two blocks, and they are basically variables that represent the starting address of the two blocks, and both of these blocks are defined in the data segment. So move instruction normally by default would transfer data from the data segment to extra segment, but here the destination is not in the extra segment, but it is also in the data segment. Block B is in the data segment. So to make this kind of transfer happen, we have to copy the value of the data segment register to the extra segment, and then the microprocessor would assume that the transfer is happening just like normal from the data segment to extra segment, but the extra segment would now point to the data segment instead. And it is important to store or to save the content of extra segment for the later use so that it can find to the real extra segment instead. To do that, we have to push extra segment onto the top of stack so that we can save it for later retrieval, and also as the source index and the source index and destination index registers would need to find to the starting address of block A and block B, we also need to save these registers as well. So the first task for the programmer is to do to write instructions so that the extra segment register is also pushed onto the top of stack, the destination index register is also pushed onto the top of stack, and the source index registers are also pushed onto the top of stack. So we these instructions would push ES, EDI, and ESI onto the top of stack. Now we can reuse these registers with different values, and then after we are done with the transfer from block A to block B, we would need to restore the original values of these registers as we would see shortly. So after saving these registers, now these two instructions would just copy the content of the data segment register into the extra segment. So push DS would move the 16-bit value in the DS register onto the top of stack, and pop ES would read back that 16-bit value stored in the DS DS value from the top of stack back into the extra segment register. So push DS would move 16-bit value in the DS register to the top of stack. Pop ES would bring that value back to the extra segment. So basically, these two instruction copies the 16-bit value and the data segment register into the extra segment. So now, as extra segment has the value stored in the data segment register, it would point to the data segment instead of pointing to the old extra segment. So now we have just reset the extra segment register to so that it would also point to the extra segment to the data segment, and the data segment register is originally having the value that is pointing to the data segment. So extra segment and data segment both now points to the starting address of the data segment. Okay, after that, now we are ready to move all the bytes from block A to block B, and for that the offset address of the block A is transferred to the source index register, and the starting address of the block B is moved to the destination address, because block B is the destination index destination. So we move its starting address to destination index register, because these are the two registers used with the string instruction. And after that, the total number of bytes that we want to move is the block size. We want to transfer all the bytes of the block. So assume that is stored in the variable block size. So we just move this block size to count register. So we load count, and after that we just use repeat prefix with MOVS D, and this D is used for the double word. So each time this MOVS instruction is executed, it would transfer 4 bytes of data from block A to block B. Why? Because this instruction transfer always transfer from the data segment location addressed by SI to the extra segment location addressed by DI, and now these registers exactly points to those locations that we want. And this repeat instruction would repeat until CX becomes 0, and CX is decremented with every repetition, as we saw on the previous slides. So this repeat would repeat this transfer instruction with each time this transfer 4 bytes of data. So for example, if we want to move 40 bytes of data, then we have to move 10 into the E6, so that this instruction is executed 10 times, and each time it would transfer 4 bytes. So 10 multiplied by 4 becomes 40 bytes. So after all of the bytes in block A are transferred to block B, this repetition instruction, or the condition would fail, and because the CX would be 0, and we would come to the controller would come to the next 3 instructions, and these instructions are just responsible to restore the original values of the registers. And as the stack pointer at this stage points to the top of stack, and that the top of that stack would store the value of source index, because it was pushed here, and when that is retrieved, the stack pointer would now point to the top of stack, which is now storing the old DI, and that is popped up from that location. And after this pop, the stack pointer now is pointing to the top of stack, which is storing the value of ES. So pop ES is used in the reverse order. So here push ES was used here first, and it is used last. So that means stack is working as last in first out fetch run. So so these instructions is transferring all the bytes of block A to block B, and this transfer is happening within the data segment of the memory. So the transfer is from memory to memory, and it is intra segment transfer. Compare instruction, as the name specifies, CMP means compare, just like the arithmetic instruction, and S means that the string data is compared. So compare S compares two sections of memory data as string bytes or string words, and in the later microprocessors they can also be string double word and string quad word. But in 8086 microprocessor, string bytes, 2 bytes or 2 words, and the two sections of memory are compared with each other. Compare S instruction is normally used with repeat equal or repeat not equal prefixes, or they can alternatively be used with repeat F0 or repeat F not 0 prefixes. The contents of the data segment memory location addressed by SI are compared with the contents of the extra segment memory location addressed by DI, just like the MOVS instruction, where the source of data is the data segment with the offset address provided by the SI, and the destination of data is the extra segment with offset provided by the DI. Just like that, here compare CMPS instruction would compare data from the data segment memory location addressed by SI with the content of the extra segment memory location addressed by DI. Here we have some forms of compare string instruction, and the first form is compare string byte, and this compare string instruction would compare 1 byte from the data segment with 1 byte of the extra segment. And to do that, the data segment, to access the location of the data segment, the physical address of the data segment must first be calculated, just like we did before. So let's suppose that address is represented with MA, that is the memory address or the physical address of the data segment. To calculate that, the 16-bit value from the data segment is taken, it is left shifted by 1 hexadecimal digit. The source index offset address is added with that to get physical address. In 8086 it's a 20-bit physical address, and then the physical address of the destination is also calculated by left shifting the 16-bit value from the extra segment register, and then the offset address from the DI is added, so a memory address for the extra segment is calculated. And then after we have the physical addresses of the source and destination, the value, the byte from the extra segment memory location addressed by this physical address is subtracted from the byte from the data segment, and the result is stored nowhere, but they modify the result causes to modify some flags. And remember that compare string byte is just like sub MAD, which is this is the physical address or memory address of the data segment, comma MAE, and this is much more like compare CMP MAD comma MAE, because with sub the destination is affected, but in compare string byte instruction the destination is not affected. So it's better to replace this SUB with CMP, which is arithmetic instruction. So compare string byte basically performs subtraction of the string byte at the extra segment from the string byte up the data segment, and the flags are affected. And the flags are affected as follows. If the byte in the physical address is greater than the byte in the extra segment, then no carry is needed because this is greater than MAE. So no carry is needed, so the carry flag would be 0. The value is not 0 because one is greater than the other, so the value is not 0. So the 0 flag is still 0 because the result is not 0. The sign flag is 0 because the sign is still positive. And if MA is smaller than MAE, then of course, as this MA is smaller, we will need a borrow to be taken. So a borrow is required. So the carry flag is 1. And as one is smaller than the other, the result is not 0. So 0 flag is still 0, and the sign flag is 1 because the result would be negative. And if the values are the two values are equal, the carry flag is 0 because no carry is needed. Sign flag is not 0 flag is 1 because the result is 0, and sign flag is still 0. Okay, so after this instruction is executed, for byte operation, depending on the direction flag, the SI and D are incremented or decremented. And for word operation, W is used, compare string W, and depending on the direction flag, SI and D are updated as it is W, so it is incremented by 2 or decremented by 2. If DF direction flag is 0, auto increment mode is set, so DI and SI are incremented by 2 because 2 bytes have been compared. And if DF is 1, then auto decrement mode is set, so DI and SI are decremented by 2 because 2 bytes have been compared.